Up until this point, we've talked primarily about the fields in free space, and we've used the constants epsilon naught, which is the permittivity of free space, and mu naught, which is the permeability of free space, to represent the parameters of the medium when there actually is no medium, when you're just dealing with vacuum. In today's lecture, what we're going to do is we're going to talk about dielectrics and magnetic materials, which are extremely important for relating the magnetic field to the magnetic flux density and the electric field to the electric flux density. We have a couple of objectives from this lecture. The first objective is that we want to know how the electric fields interact with materials, what happens when an electric field interacts with a material, and ultimately how that allows us to get to the dielectric constant, which is the quantity, the macroscopic quantity that we generally use to describe a dielectric. You need to be able to apply these electric properties when you have a material in order to be able to solve problems in simple media, and I'll define what I mean by simple media in the course of this lecture. And you don't need to be able to derive the physics behind permittivity. You don't even really need to be able to work out problems like that. But you should understand what sort of interactions are going on, because this can help you when you get to more advanced problems like waves interacting with the ionosphere or nonlinear materials or things of that nature. On the magnetic side, very similar set of objectives. We want to know how magnetic fields interact with materials, and the same sorts of levels of understanding. To be able to apply magnetic materials to solve problems involving waves and understand a little bit what's going on. It turns out that magnetic physics is much less well described and understood, and so we're going to brush on past it and just describe it all in terms of one simple constant. First thing we're going to do is we're going to talk about what happens when an electric field interacts with a charged neutral material to give rise to polarization and permittivity. We're going to use a fairly simple model that refers to our knowledge from chemistry. And what we have are a bunch of positively charged ionic centers that make up the lattice of the material, and then there are electrons which are distributed around those centers, and the distribution of those electrons is dictated by the chemistry of the material. But the total negative charge in these electronic shells is equal to the total positive charge in these ionic centers. And on average, the displacement between those negatively charged electrons and the positively charged centers is 0. But when I expose this material to an external electric field, and in this case we're going to be talking about a static electric field E, the wavelengths that we're dealing with are on the order of say hundreds of nanometers for optical wavelengths, or even millimeters or centimeters for radio wavelengths, and the molecule and atoms we're talking about on this order of angstroms or nanometers. So we can treat the fields quasi-statically. There are some changes that we'll need to do, and we can talk a little bit about what happens with dynamic cases, and we can do that as we come to later on. But for now, we're just going to look at statically what's going on. So I apply an electric field, and that electric field, of course, is going to impart a Coulomb force on the electrons in the ionic centers. But we're going to make the assumption that the centers can't move, because they're much more massive and because, say, they're more fixed in space due to their binding. But the electrons, which are orbiting these ionic centers, can shift statistically in space. And so we end up with a shifting of the electrons, where I have the negative electrons more likely to be found in this region than down they were before. So now, on average, I have a net displacement between my electrons and my nuclei, and that gives rise to an electric dipole moment that we call P. And that electric dipole moment points from the negative charge to the positive charge, as we know. And of course, that induced electric dipole moment is going to impart a magnetic field. The imparted magnetic field, the induced dipole moment is going to give rise to an imparted electric field in the material. The quantity that we are interested, though, in is not these individual microscopic electric dipole moments, but it's the average dipole moment, or the dipole moment per unit volume. And so we can define that this way. I can take some volume over here. Say I'll take a volume here that has some volume element dV, and I'll count up how many dipoles there are inside that volume. And this vector P, this vector field P, the polarization, will take as the limit as the volume goes to 0, the sum of these dipole moments. Of course, the dipole moment is equal to Q times D, right? So P equals Q times D. That is coulombs times meters. And then I'm going to divide by a volume, right? So this quantity here has units of coulombs per square meter. And we can take this quantity and we can say that for a particular class of materials that we determine simple materials, or these are materials that are linear, isotropic, and homogeneous, that the induced polarization is equal to some constants times the applied electric field. And this constant we call the electric susceptibility. And so I have an induced average dipole moment, and that's the susceptibility times the applied electric field. By linear, we mean that if I double the applied electric field, I'm going to double the induced polarization. By isotropic, we mean that the direction of the P vector is parallel to the direction of the E vector. And by homogeneous, we mean that this susceptibility is constant in space, or at least over a region of space. I can have a boundary between materials with different susceptibilities. But over a region of space, the susceptibility is constant. None of these assumptions are particularly sacrosanct. We absolutely can have nonlinear materials, very important in optics especially. Many materials are anisotropic, which means that the induced polarization is not necessarily parallel to the applied field. And most materials are actually not homogeneous. And we call this quantity here, this chi sub E, the susceptibility. And you think how susceptible is the material to being polarized when exposed to an electric field. Well, the effect of this induced dipole is to create a field that opposes the external field. But the total external electric flux must be conserved. And so we can define this displacement vector, and we've seen the displacement vector before. It's one of our fundamental quantities. Of course, it has units of coulombs per square meter, and we define this displacement vector as the permittivity of free space times the electric field plus the polarization. Now, if I'm in free space, this polarization is equal to 0. And so D equals epsilon naught E. But if I am in a material, I have something a little more complicated. We, of course, know that the induced polarization is epsilon naught times chi sub E times E. And I can gather all those terms here, and I can write that as epsilon naught times epsilon sub R times E. And epsilon sub R is the relative dielectric constant, or relative permittivity of the material. And so, for example, oil or many types of plastics have dielectric constants around 2.3 for microwave radiation. Glass has dielectric constant of about 2.3 as well at optical wavelengths. Water has a dielectric constant of around 81 at microwave frequencies. So these, when we're describing different types of materials, we'll talk about what is their dielectric constant, and we'll give a number like 2 or 5 or 81, and what we're talking about there is the relative permittivity of the material in question. One important thing to take in mind is what happens as I get to the edge of the bulk material. Now remember, our material here is charge neutral. I've got just as many negative charges as positive charges. So if I draw a box outside my material, the net charge is equal to 0. But as I apply an electric field, I get this elongation of my molecules. The electrons are still bound. They're not going anywhere. They're not free to conduct current. Okay? But they spread out. Now, the fact that these electrons here have moved a little bit, and I have a little bit of extra negative charge in this location, that's compensated by the fact that some of these electrons have left. Right? And so inside the material, when I have a homogeneous material, the net effect of induced polarization does not create any new charge. But when I get to the edge of the material, right, there's nothing to compensate, and I actually end up with a buildup of negative charges on one side and positive charges on the other side due to this displacement. And more generally, we have a bound charge density that we call rho sub bound. and that's equal to the divergence of P. So if I'm in a region where P is varying spatially, that gives rise to some effective charge density that affects the electric field, even though it's not free charge that can move. But since we're going to be dealing with homogeneous materials where the dielectric constant is fixed, the bound charge is generally going to be 0 except near the interface. We can have a similar conversation for magnetization, the magnetic field, and the quantity that we call permeability. And so in this particular case, I've got electrons not only have a charge and associated orbit, but they also have a spin associated with them. There's also some angular momentum associated with their orbits. That angular momentum gives rise to a bunch of little local dipole moments. When I apply an external magnetic field, the dipoles want to align themselves or anti-align themselves with the magnetic field depending upon their nature. Turns out that the physics of magnetic materials is much more complicated than the physics of electric materials, and we're not going to go into it in any great length. But for simple materials, we can write the induced magnetization, which we describe by this capital M, as chi sub m times the applied magnetic field intensity, and this is the magnetic susceptibility. We have a very similar relationship relating the magnetic flux density to the magnetic field. We can write B equals mu naught H plus mu naught M. Gathering our terms, we have this 1 plus chi sub m, and just as we did in the electric material, we can describe a relative dielectric constant, 1 plus chi sub m, and we call this the relative permittivity, the relative permeability of the material. Most materials actually have a relative permeability which is a little bit less than 1. Their susceptibility is actually a little bit negative, so that means that the dipoles have a tendency to anti-align with the magnetic field. You can read through your textbook and you will see that for most materials their relative permeability is like 0.99995 something. But a class of materials which are ferrous materials, iron being the most common, but there are ferrites and other types of metals that have this property, you can actually have very large permeabilities, mu sub r's of several thousand. And what this means is it gives you a very strong concentration of the flux. And so, for example, if you're making a transformer, you will wind a coil of current around an iron core. And that iron core very much concentrates the magnetic fields, gives rise to a very large magnetic flux density. And in point effect, you can turn off the current, and that magnetization remains in the material, and that has to do with the physics of how that material is put together. We're not going to go into this at all. These are just concepts that are important to you if you end up working with permanent magnets, or they're important if you end up working with rotary machines or generators, and if you ever get to that, you're going to need to refer back to your textbook. So that brings us to the end of this particular lecture, and we're not going to ask any specific tutorial questions for materials. We are going to use materials throughout the course, and we're going to apply them very much immediately in the next lecture, where we talk about boundaries between materials. And so the tutorial questions that sort of test 4A are really going to come in the context of lecture 4B.